I think I'm back. Please, somebody say hello to me somewhere. It's been almost a full 45 minutes since I started. I'm having so many technical difficulties. I don't even know if I'm just talking to myself. People are saying yay, yay, woo, so that must be. I don't have the chat, so give me a second, everybody. Welcome, good morning, good afternoon at this point. My name is Dan. I am a person who likes honeydew melons. If I can open this up. It's gonna soothe me. Good. Well, I need to get the chat going. So let me see if I can get that going over here. Am I live now? I see myself. Pop out chat. Close this. Did I get a new member? Someone with the initial D? Welcome, Dev. Okay. Okay. Whew. Take two, everybody. You know, maybe I'll come back and do a little Q&A. I'm not going to do that Q&A thing again. So if you, for some reason, you are watching this as a recorded archive, I just live streamed for a little bit. I think that live stream from earlier is just going to wander off into the unlisted category forever. This will be the beginning of today's Coding Train live stream. Hopefully, that nothing will crash. I will just be here and I will enter the fourth dimension. Production values, animations, music, all that stuff that I don't have. All right, so I'm still getting myself a little bit organized here. I do like watermelon, as is also being asked. People say they don't like melon, and I've mentioned this before. A good, freshly cut, ripe melon is delicious. It has very low acid. It's soothing. It's healthy. What could possibly be wrong with melon? Blueberries are my favorite, though. I'm about the fruit thing. Okay, so let's just begin with the fourth dimension. Except we need to begin. I got to work up slowly to that. So let me open up the browser. I don't need this. Do I need this one? This ML5 thing that I was talking about, I will come back to it another time. And I'm going to leave up here, Understanding 4D, this Tesseract page. Actually, I want this to how do I not get it to autoplay off? So I guess it's playing anyway. I don't know. I wanted to just load the page with the thumbnail, but that's fine. We'll make a thumbnail. Yeah, this is pretty good. All right. Then I need to open up processing. Oh, I need to get a new version of processing. So the processing 3.4 came out. Let me briefly download that. If you're not familiar with processing, it is a Java-based program environment. Don't worry, that's the usual problem that I have. Nothing new here. We're going to draw a four-dimensional melon. That's a great idea. Did I break Facebook? Thank goodness. What's popping up here? Nothing. Mac OS X is what I am, and oh, it's already downloading. I'm silly. Please support the Processing Foundation if you are if you have the ability to do that. All right. Let's move this over here. Replace. Quit. Replace. Open. Yes. Okay, here we go. All right, so here's the thing. I want to matrix. Just No. What's that website that I like? Matrix multiplication.xyz maybe? Yes. Three-dimensional point, and I want 3. This is what I want. No. I want this. I want 3, and then I want 2. That's no. Why won't it? Because it's to the columns. Oh, does it need to be? Oh, I'm doing this backwards. And then, whoops. There we go. That's what I want. Sorry about that. And can I make these any numbers I want? Okay. All right, everybody. Let's see if this camera's working. Nope. Let's see if this brings it back. All right, so I don't know where, this might not have a place in a playlist anywhere, but I'm going to do 2 coding challenges, one to render a 3D cube in 2 dimensions, and one to render a hypercube of 4 dimensions in 3D, which is actually rendered in 2 dimensions. So those are the 2 coding challenges I'm going to do. I need to have a function in processing which will do matrix multiplication for me in order to do these challenges. So I am going to quickly, I meant to do that actually before I started, I'm going to quickly code a simple function that just takes 2 two-dimensional arrays in and returns a new 2-dimensional array with the result of matrix multiplication. All right, so that's what this first video, which may or may not even be a video, separately edited video, I don't know yet, but I might as well talk it through while I'm doing it. Hello, this video is about just matrix multiplication. That's the only thing it's about. And I'm going to show you, I'm going to write a function to do matrix multiplication with simple 2-dimensional arrays in processing, which is the Java programming language. So really I'm writing a Java function to do matrix multiplication. Now, if you want to know a lot more about matrices and matrix multiplications, I'll refer you to the 3 Blue 1 Brown series on linear algebra. But I also do have my own videos where I code a simple matrix library in JavaScript. But this video is in anticipation of doing some 3D graphics in 2D, so projecting a 3D shape into 2 dimensions. And so to do those tutorials, I need a function that will do matrix multiplication for me. So if you're watching this, this is why. So what is the matrix? That was no good. Edit that out. All right, so a matrix is a 2-dimensional table of numbers. So for example, this is a matrix. Now, this is, by the way, what's often referred to as the identity matrix. This is a matrix that when you multiplied this matrix by, hold on. Where's my fancy new eraser? People are complaining that Java's a bad language. There's so much. Hold on, I'm just looking for something. I know I'm over here, but just give me a second. Where is it? I can't find it. That's fine. I bought these new erasers. Here we go. Here we go. When you take one matrix and multiply it by another, let's say this is the other, and I'm going to write x, y, z here. The number of columns of the first matrix must match the number of rows of the second matrix. And you can't see me writing that. I'm really off my game here. At least the stream appears to still be working. The number of, when I perform matrix multiplication, it's so noisy. Can you hear the furniture being rolled back and forth in the hallway? Let's see if that quiets down. Now, ordinarily when we're talking about multiplication, let me just it's going to be amazing if I ever make it to the fourth dimension. I'm going to make it to the fourth dimension, and then I'm just going to... This is kind of interesting what this does. What happens if I spray some water? Ooh, that's good. Ooh, this really cleans it well. So do I do it with this side? That's the wet side, and then this side is like the dry side? Maybe? Who knows? All right. And take 479. All right. Don't worry. This is going to start to move along. Oh, wait. I'm getting an interesting comment from Adam J. Austin. Doesn't that need to be the 3 by 3 matrix to be an identity? Yes, that's the 2D identity matrix, though, with just... I guess let me look at what I did. Hold on, let me check something here. Yeah, but it's my sense of what I'm talking about. Well, I won't mention that this is the identity matrix for 2 dimensions. So if I want to project a 3-dimensional point into 2 dimensions without stereographic perspective, then this is the matrix I would use. Yes? Or square. Good point. Okay, fine. Well, I'm starting over. But I don't need, this would, yeah, identity would be, so my terminology is wrong, but because this would be, oops, no. This would be the identity matrix, but what I'm doing is so for it to be a 2D identity, it needs to be a 2 by 2 matrix with 1s down the diagonal and 0s in other places, yes. So this is the identity matrix for 3 dimensions. So my terminology is incorrect. This is a projection matrix that just eliminates the z. So I don't, maybe that I can't call that an identity matrix. But if I go to orthographic projection, and here we would see, oh, I guess technically I should be putting, but I feel like these don't matter, right? Because that's just going to give you 0. So the way I always do it is just leave that out. And this is not identity. So it's not an identity matrix. And then actually this is for like the projection. There's more to it than this. Okay. Yes, you're right. Shade in the chat is making a very good point. 2D shadow of a 3D object, aka square. All right, everybody. I won't use the word identity. I'm glad. Okay, so. All right, so what is a matrix? A matrix is a two-dimensional table of numbers. For example, this is a matrix. And I could write, I'm gonna write 3 zeros down here just for one. No, you know what? Just for demonstration purposes, I'm gonna leave it like this, because this is actually a matrix that I'm going to use in my code itself. This is a matrix. It is 2 rows by 3 columns. Okay? Now, I'm going to show you, here's another matrix. Here is another matrix, and I'm just going to write x, y, z. This matrix is 3 rows by 1 column, right? And so one thing that's very important is that when you do matrix multiplication only works if the columns of matrix A match the rows of matrix B. And you can see those match up here. Now, what do I mean by matrix multiplication? How do we multiply these two things? Normally, when I say multiplication, I might mean something like, 2 times 3, which equals 6. Or I could even do something where, I have these two, what if I did something like 3, 1, 4, and I just said 2, 2, 1? You could almost think of multiplying these and getting a new matrix that's 3 times 2, which is 6, 1 times 2, which is 2, 4 times 1, which is 4. But that's not matrix multiplication. This is what's known, what I just did here is what's known as element-wise multiplication. It's not what I'm talking about here. What I'm talking about here is matrix multiplication also relates to something called the dot product. There's too much to talk about forever and ever in this video. I really just want a function to perform matrix multiplication with this. And what this does is basically the way that this works is you matrix multiplication, which is not really like a good symbol for it, so I'm just going to write matmul right here. Basically, I'm going to take this row and multiply it by, is that right? Yes. Yes. Yeah. Okay. So, I got confused here. I'm going to take this row and multiply it by this column. Sorry, I'm just confused here. If that had 2 columns, it would still, the number of rows. Hold on. Boy, I already made a whole video about matrix multiplication, and I said to myself, I never want to do this again. I've done it so many times, but we're going to do it again anyway. All right, let's actually, okay, I want to do matrix multiplication. Let's go back to that web page that I was at the beginning. And I'm going to press multiply here. Let's see what happens. Whoa, oh my goodness, Look at that. It went up and then went sideways. That's interesting. Let's go to next. Woo, oh, look at that. So what just happened there? Look at this. I am going to take this row and multiply it by this column in a way that this number gets multiplied here, this number gets multiplied here, this number gets multiplied here, and they all get added together. So what I'm going to get is 1 times x plus 0 times y plus 0 times z. X. Now I'm going to do exactly the same thing. We can confirm this. Then we do exactly the same thing for the second row. Press this button. I'm going to take 0 times x plus 1 times y plus 0 times z, and I'm going to get y, and then I am done. So 2 by 3 matrix multiplied by a 3 by 1 matrix results in what? A 2 by 1. 2 by 1 matrix. Now, so this is the basic idea, and this is actually the reason why I'm showing you just this one scenario, is this is what's going to happen over and over again in the videos I'm about to make about taking a 3D point with an x, y, and z and projecting it into 2 dimensions. And what this matrix actually just did is just eliminate the z. It's as if I am looking straight on at a 3-dimensional object, and I just can't see the z at all. Okay. So now, let's go and write the code to do this matrix multiplication. Yeah. So Mobius in the chat just put it better. It's a 2D shadow of what I'm looking at here is the 2D shadow of a point in 3D. Okay. So now, let's open up processing, and so how am I going to make a matrix? So I'm going to call this first matrix, I'm going to make it a 2-dimensional array, a projection, and I can just say, what did I say, 1, 0, 0, and I'm going to format it in my own goofy way, 0, 1, 0, and then I'm going to say float point equals, now this is silly, but I'm going to do 100, 75, 50. Okay, so let me just do this. And let me do matrix multiplication. All right, what's wrong here? Need another bracket. All right, so you can see, and I guess if I want to be consistent, I could do this. And there we go. So these are my 2 matrices. I have this one, and I'm just storing them as 2-dimensional arrays. And I'm basically the first array, the first index is which row, and the second index is which column. Okay? So that's what I've got right now. So now I need to write a function. I want to write a function which is going to return another 2-dimensional array. I'm going to call it matmul, and it gets, as its arguments, 2 1-dimensional arrays. Now, here's the thing. I'm looking at the chat. What did I do wrong? Yeah. Okay, so this is my function for matrix multiplication. Now it's complaining at me. What is it saying? Oh, it has like some errors. I don't see any errors. Line 8 has an extra space. Oh. Thank you. I'm just looking. Why? Hold on, let me just see something. Oh, but it's not void. I'm like losing my mind because I don't know Java anymore. Okay. It's just because I haven't returned anything, right? No? It should be fine as a local. is so weird. Have I just like forgotten Java completely? Oh, it's just a weird processing thing. Oh, okay. All right. Okay, ignore me. I'm back. Oh my God. Oh, this is horrible. This is horrible. Been here already an hour. I'm like nowhere close to this. Okay. All right, first, since I'm in processing, let me just add a setup function here. Because the idea is what I want to do is I want to say float result, being a new matrix, is something like the result of matrix multiplication between the projection and the point. Mat mul. So I need to write my own function. Of course, it's complaining at me because it doesn't know what this is. I need to write my own matrix multiplication function. So I'm going to go ahead and do that right now. And I'm going to say, this is a function that's also going to return a two-dimensional array. And it's going to take two matrices in, which are two, and then it's got to return something. So let me just add return null at the bottom here. So now I should have no errors. No errors. So this is what I want to do. I have projection, point. I want to be able to matrix multiply both of those and get the result. So how do I do that? Well, one thing I need to do is I need to know columns A is A dot right. Okay, now how is it A dot length? And then rows A is A index 0 dot length. Does it not let me do that? Yes. Okay, so in other words, I first want to figure out the columns and rows of each one of these because that's going to be pretty important. Now, it's a two-dimensional array. So if I say index 0, the length, that's the number. Oh no, so this is the columns. This is the columns, right? The number of things in it is the number of rows. Right? We can see here, like just point dot length is 3, point index 0 dot length is 1. So that's the columns of A, and now the columns and rows of B are B dot 0 dot length. Now this assumes that there's at least one thing. So an empty matrix, this is going to give us an error, but big deal. Now the other thing that I need to look at is I need to make sure that the number of columns of A matches the number of rows of B. So if columns A does not equal rows B, then I'm going to just like return null and maybe print line columns of A must match rows of B. Okay, so now we have a little. And then now, assuming that everything's okay, I can now say float result is a new array with the number of, this is so hard, the number of rows of A and the number of columns of B. The number of rows of A and the number of columns of B. Okay, so now we can just go through, just pause for a second. There's a great comment in the chat. Why would they be float? I'm pretty sure dot length is an int. Yes, these should be integers. There's no reason to make them a float. In fact, it's only going to cause me problems. I'm just so used to programming in JavaScript where I don't have to worry about this stuff. And so to me, float is like var, let, that sort of thing. But great point, or const. Okay, so that's a really great point. Now, pause again for a second. So what I need to do, first of all, is I need to fill every single spot of the resulting matrix. So I need to go through all of the rows And then I need to go through all of the columns. Whoops, result. Oh, wait. Yeah, result. This is silly because I could just use rows A's and columns B, but I'm going to, oh, these don't have, sorry. I need to go through all of the rows, which is rows A, and all of the columns, which is columns B. Sorry. I was imagining like in my previous, and this is 4, I made this matrix library. So this could be the beginnings of a matrix library, potentially, if you wanted to write your own. Have fun. Have at it. I'm like Sisyphus, and I just program the same stuff over and over again, and I make the same, and then I get all the way up to the top, and my matrix thing works, and then the matrix multiplication rolls all the way down to the bottom of the hill. I forget how it works completely and have to like push it all the way back up to the top again. This is my life. All right, so, okay. So now what I need to do is now do that dot product. The reason why I say dot product is really, what this is it's the dot product of these 3 numbers with these 3 numbers. So I need to take row from one and the row and the column here. Okay. So what I'm going to do is, so the dot product needs a sum. So I'm going to say sum is 0. Then I need to go through all of the columns again. I guess I'll call this K. Columns B. And then I need to add up. What do I need to add? I need to add I need to add this, which is in position, well, it's in position 0, 0, but that's really position IK, I think, plus A, I, K times B, K, J. Does that make sense? Right? Because I'm going through all the columns of B, all the rows of A, and then K is just moving me along all the columns of A and all the rows of B, right? This is, so I'm going to go through, I'm in row I, and I'm in column J, and then I'm going to take K, which from row I times, from column I times row J. Oh, are you watching this? I'm so sorry for you. This is right, though. I actually think I have this right, but basically, let me actually make this more clear. This is row I, column K. And so when row I is 0, K is the thing going up. This is row K is the thing going up, column J, which is fixed here, just 0. So look at that. This should be what I have here. I want to take and multiply, add all those things together, and guess what? You might have to pause this video and make sense of this yourself. I should have practiced this. The result, I, comma j, is that sum. So now, I should be able to say return result. Result. Oops. Return result. This is, by the way, what happens when you don't have NumPy. Your life becomes, I'm sure there's plenty of matrix libraries for Java. I just can't bring myself to use them. All right, first let's just run this and see if I get any errors. So no errors came up. That's good. I want to write a function. I'm going to call it log matrix, or let's call it print matrix. Oh, that's already a function in processing, actually. Oh, it's just so great. We get to show that later. Oh, this is so exciting. Okay, I'm just going to call it log matrix. And it's going to get matrix M. And then first I'm just going to get the columns and rows. Columns and rows. And then I'm going to print line columns by, rows by columns. Then I am going to print line some nonsense. And then I'm going to say, I'm going to do this nice little loop again, this double loop. And this is rows, and this is columns. And I'm going to say print matrix row column plus a space. And then when I get to the end, I'll do print line. And now what I should be able to do is I should be able to say, to test if this works, I should be able to say log matrix projection, log matrix point, log matrix result. So now let's see if anything I did worked correctly. All right, let's look. Oh, no, it's wrong. Well, I'm gotten close. So, okay. Oh, first of all, let's do an extra, I need an extra print line in my log function. Let's do when it's done, let's do an extra print line. Okay, let me run this again. So I have some mistakes. So the good news is this is right. 2 by 3. This is a 2 by 3 matrix. And that looks right. This is a 3 by 1 matrix. 3 rows, 1 column, that looks right. And the result should be, oops. And the result should be, oh wait, hold on. A 2 by 1 matrix, 7550. Now, not 7550. I've used different numbers. It should be 175. I mean, technically, if I want to match that web page, let me go back. How can I go back? No, whoops. Okay, whatever. You get the point. I've lost everything. Tesseract. No, don't. The Tesseract is coming to get me. What was I doing? This should be, we know this should be 175. That's what I should see. Right? 175, x, y. So something is wrong in my matrix math calculation. So let's look at this. I'm staring at it as if that's going to help. Hold on a sec here. Look at some other code I wrote the other day. Rows A, columns B. Oh, this should be, this is columns A. Let me just make sure that's right. Yeah, whoops. Okay, that's the mistake. Okay, I found my bug. This right here, this is the bug. This is the offending line of code, columns B. Why is that wrong? That is wrong. That is most definitely wrong. Let's go over and look as to why it's wrong. Remember how I was saying K is counting through each column here and then counting through each row here. That's the whole thing that has to be equal. 3 columns, 3 rows. 3 columns, 3 rows. So that number could either be columns A or rows B. Either one of those things. Is that what I put in there? No. So this should be columns A. It could be rows B. That would also work. And I am now going to run this again. And voila! We performed matrix multiplication. Now I need one more helper function. If you will bear with me. What I need now also, I'm going to need this for the future. In these videos that I'm intending to make, I need a function, because I'm going to use p vectors a lot. So a p vector, by the way, like p vector v, is typically how I'm going to want to represent a point. So if I want to represent a point, I don't want to have to write it like this all the time in my code. That's going to be a major pain. But if I want to do matrix multiplication, I'm going to want some tool to convert from a point to a p-vector to a matrix. So I want a function vec to matrix that receives a p-vector. And then I want a function, probably also matrix to vec, that receives a matrix M. So let's write both these functions. So this should be pretty easy. I just want to create a matrix which is, it has three rows and one column. And then, I'm going to be really lazy about this. I'm going to say m0, 0 equals v dot x. And then, I can't type 1 and 2, v dot y, v dot z. That's useful. And then I just say return m. Then I'm going to write the other function here now, which is, I'm going to say p vector v is a new p-vector, and v dot x equals m. What am I saying here? Which is m 0, 0, v dot y equals m 1, 0. Now, I might get some matrices back that don't have that many rows. So only if m dot length is greater than 2, then I can say v dot z equals m to index 0 and return v. So assuming these helper functions are written correctly, now I don't need this. I'm going to take this out, and I'm going to say, where's setup? I'm going to say float point equals vec to matrix V. Now I can do that. Then I also want to say, just to be sure, I'm going to say, I'm going to say, now I'm also going to say p vector v equals matrix to vec result, and then print line v also. Okay, let's run this now, and we should see, what do we got? So I have my 2 by 3 matrix. My vector got, so I really, just to be clear about this, I should probably say right up here also print line v. So just to see that everything worked. This is my p vector, 175, 50. This is my projection matrix. This is my p vector converted to a 3 by 1 matrix. This down here is the result of the matrix multiplication as a vector. And this down here is that same result. All of this to just take the z component out. But, oh boy, we're ready now. We're going to have rotation matrices. I'm ready. I'm ready to move from the first dimension to the second dimension. So I look forward to seeing you. You can check this video's description for links to where I actually do 3D rotations in 2D and then eventually 4D rotations in 3D. See you there. Kelly asks, can you just overload matmul that receives a point, then converts it to a matrix, then calls matmul to call the other one? Yes, that is a great suggestion. That is a great suggestion. Let's do that. All right. Oh, one more thing. Suggestion from Kelly in the chat. In terms of making a useful helper function, it would be really nice for this here to be, right, the first thing that's passed in, the second thing is the vector. So I should have an option where this is a vector, and then I would just say I could just quickly, this is overloading the function. I'm writing a same version of function, but with a different argument. This is how this is done in Java. I would say vec to matrix B, and then I would say return mat mul a m. Right? So if I do that, then now I can get rid of this line, and I can just say v here, and I should have the same result. I'm going to get rid of this log. I don't think I need these logs anymore, just to make sure it works. Yep, so that worked. We can see that worked as well. So this makes our life a little bit easier. Now, again, this is by no means comprehensive in terms of matrix mathematics, but I happen to know that for the next video I'm going to make, where I'm going to take 3D points and project them into 2D, this is all that I need. Okay, see you in the next video, which I will link to through the magic of the linking of the things. All right, everybody. We're getting closer. So one thing I want to do is now just take all these functions, and I'm going to make a new sketch. I'm going to call it a 3D projection 2D, or I'm just going to call it 3D into 2D. And of course, one thing you should know about processing, because processing makes Java classes, you can't start a Java class with a number, so it actually renamed it for me sketch underscore, which is absolutely fine. Then I'm going to make a new tab. I'm just going to call it matrix, and I'm going to put all this stuff. Vec to matrix, matrix to vec. I don't need this here. Log matrix is useful, and then the matrix multiplication functions. All right, everybody. Okay. We've got a little momentum now. I'm going to come over here and erase the whiteboard. The question is, do I have any props? If I had a nice like cube. Oh boy, I don't know about this. I don't know about this. I was promised perfect, clean whiteboard erasing. Sustainable, eco-friendly, perfectly clean whiteboard erasing. This doesn't seem to be working out. But maybe if I now switch to the other side, have I done this wrong? Am I using, oh no, that's nice. Was I supposed to use the other side first? I don't know which side is which. Should have read the instructions. Okay. Okay. I'm curious, is anybody in the audience who actually happens to have been watching all of this, never done matrix multiplication before, but kind of knows processing, were you actually able to follow that? I would like to know. All right. Simon wrote a message about PZCam, which is interesting. Luke writes, yes, so I did see that. I'll have to research that. Thank you. Maybe share some more information with me about that after the stream. Get Expo spray. No. You see, I bought these things because they say they don't need any special spray. They just work with water, and I want to not, I don't know, poison the world. All right, so now. All right, now I need to code something up really quickly. So what I'm going to do right now is I'm going to create a sketch using the P3D renderer. and I'm going to say box 100, and I'm going to say float angle equals 0, and I'm going to say rotate x by angle, rotate y by angle times 2, and rotate z by angle times 3. And then I'm going to say angle plus equals 0.01. We're going to run this. Oh, and I'm going to say stroke 255, no fill. And I'm also going to put it in ortho, because I'm going to do orthographic projection. Okay. And just to be clear, let me also make the stroke weight a little bit brighter. Okay. That looks pretty good. I feel like this should be bigger. Let's make the box 200. Maybe make this 4, just in terms of people being able to see it. Okay, great. Now I'm just curious. I'm going to comment out ortho for a second. Whoa. Actually, I kind of like having ortho in there. That's crazy. Oh, it's because I didn't really set it back or anything, but that's fine. Okay. Now, let's go here. Yes. Okay. All right. Great. This is all I need. Okay. I think I have everything I need. This can go further over this way to here. So then the browser can go over here. All right. Let me know if I am back with the message, in particular in Slack, because I do not have the YouTube chat open, although I'm about to try to open that. In theory, recently closed. This should get me there. Back. Okay, great. Sorry about this. I really wish I knew what was going on. Some days this just happens constantly, and other days I stream for hours and hours and this doesn't happen. I should mention that I have raycasting eventually. I should mention that I have a meeting at 2 p.m. I didn't imagine I'd be streaming from 11:30 all the way up until 2. I will come back after that meeting. I'm going to finish this today. I'm not going anywhere until I finish this. But I will have to take a break. And I think since I had to stop and start the stream so many times, unfortunately, I think YouTube will only blast 2 such and such channel is live notifications per day. So I may have used up all of mine. So for when I come back, I will create an event. You're just going to have to check a little bit more manually. Go to the homepage of the coding. As soon as this is done, I'll just schedule probably 4 o'clock Eastern time is when I will return. To be clear, I'm not leaving now. I still have another 45 minutes. Then I'm going to take a break, have a meeting, eat something, and come back. Yes, okay. Oh my goodness. I knew I should have never done 4 dimensions. All right. So I don't know where I last left off, but I'm just ready to just move on. Okay. Hello, welcome to a coding challenge. And I can summarize this coding challenge very quickly in 1 sentence. This is a spinning cube. It is a 3-dimensional cube that you are seeing on your 2-dimensional screen. I am able to create this three-dimensional cube because I am using the P3D renderer. Processing, Java-based creative coding development platform thing. I can make 3D stuff using the P3D rendering engine and then functions like box and rotate X and rotate Y and rotate Z. And that is how I get this. But how does this really work? How does the processing even make this happen? I am going to do the most basic simple thing. I said one sentence and I'm like 12 sentences. I'm like 200 sentences in if I'm being perfectly honest. I am going to change this from P3D to P2D. I'm going to eliminate all of the 3D rendering capabilities. I'm not going to allow myself to use any of them, and yet I'm going to recreate exactly the same visualization. I'm going to do matrix rotations, projections, those types of things. So this is not going to be comprehensive, like how to build a 3D engine with ray casting or ray tracing and lighting and shadow and all sorts of like complicated stuff. I'm going to just do the basics just to create this 3D illusion in 2D, really because if I can use the P3D, if I can create the 3D illusion and render it into 2D space, what if I create a 4D shape and then render it into P3D space, right? If I can project a 3D object into 2D space, there's no reason why I couldn't project a 4D object into 3D space. And then I don't know, my computer's gonna melt and I'm never gonna make any videos again. But let's just stick with this. That's what I'm gonna do in this video. Okay, people are asking about the melon. This will have to be a little edit point. This, my friends, is otherwise known as space melon. It is a special invisible melon that I like to eat, but really, oops, shoot. It just looks like this, okay. It's honeydew melon. All right. All right. Okay. Okay, so let's begin coding. So I am going to take out, I'm going to hit save, and I'm going to take out all of this 3D stuff. I'm going to leave translate, stroke weight, no fill. I'm not going to be able to use these anymore. I'm not going to be able to use these anymore. I'm going to leave all this. And I'm in P2D. I'm going to take out P2D. It's nice to sort of say that. The default renderer is also a 2D engine, so I don't need to actually say P2D. Now, I should also mention that in this particular video, I'm making use of a few functions I've previously written. I actually might have a video. I definitely did it on a live stream. So either way, in the video's description, I'm going to link to where you can watch me code all these functions. But what these functions are for certain matrix operations that I'm going to do. Don't worry. I will talk about what they are when I use them. So the first thing that I want to do is let me just get some points on the screen. How am I going to do this? Let me make so I'm going to make pretty heavy use of the p vector object, and I'm going to say I'm going to make a array of p vectors that just has 4 points in it, and I'm going to say points index 0 is a p vector at, and I'm just going to build a little square. So I'm going to say the first one is at like -50, -50, and then the second, third, fourth is at 50, -50, then 50, 50, then -50, 50. These should be the 4 points of a square. So what I want to do here now is just say for every vector in points, just draw a point at v.x, v.y. So now, but these are, the whole point of what I'm doing is I can't do this, right? These are, okay, so these are actually going to be 3D. The point of this is they're going to be in 3D. Bear with me for a second. Well, all will come to pass. Those are going to be 3D points, but right now I haven't done anything 3D yet. Let's make the stroke weight quite a bit bigger so I can see them. There we go. So those are my 4 points. So first, what I will need to do, and actually, I'm not going to worry about this part right now. Okay, so what do I need to do to make a 3D engine? Okay, here's the thing. I'm going to search for some props. Bear with me for a second, people. What's the chance that I have a clip light? I don't think I have a bulb in it. I'm looking for, like, this would be good, like if I could like make a shadow. Oh, wait a second. Have this, also have this LED lighting fixture that I could potentially use. Look at this, right? I could use this to make a shadow. It needs batteries, 1, 2, 3, 4, 5, 6. I only have 4 batteries. Okay, that's not going to work. It does have a plug. Oh, wait, I could actually just use, I don't want to mess with this. Maybe I'm just going to, I know, draw. I was going to try to use props. I was going to try to use props, but I think that's not going to work. What am I trying to explain here? I want to talk about projection. Okay. I'm thinking about this. All right. Use your cell phone flashlight. Thank you. That's a good idea. Hello, everybody. Look, I have a Cody train sticker on my cell phone. Train whistle, shadow. Let's see. Turn the lights out. Oh, yeah. Can you see that? Kind of works. I mean, it works if I do this, but this is not square. Oh, random number book could be good. Okay. All right. Okay, I found some props. I'm actually going to turn this light off too. And I'm going to try to do a demonstration in the dark. This is a 3D object. It is the book, 1,000,000 Random Digits with 100,000 Normal Deviates. The way that a 3D object is rendered on a 2-dimensional screen is through something called a projection. That projection you can think of as basically like a shadow. So if I have this book here and I shine this cell phone flashlight, you can see that there's a projection onto the wall. It looks like a square. If I rotate this, it rotates. If I rotate it around the y-axis, well, actually, I'll have to do this. If I rotate it around the y-axis, you can see it starts to become thinner. I can rotate it around the x-axis. It does this. So, so this is the idea. I need to create this same exact. I need to create that same exact idea, but in code. And the way that that's done is with something called a projection matrix. So the point, the 3D point, is actually something like this. It's a matrix that has x, y, and z in it. This is actually 3 rows by 1 column. This is something that I've gone over in other matrix math videos, and here's a kind of a summary of it. A projection matrix, if I'm projecting into 2D, right? If I'm projecting this 3D point into a new 2D point, I don't know if using the little tick or prime symbol there makes sense, but what I need is a projection matrix. Now here's a really simple projection matrix. This projection matrix has a 1 in the x spot, a 1 in the y spot. X, Y, Z, X, Y, Z, and it has both zeros in this sort of Z column here of this projection matrix. What this is actually always going to do is give a two-dimensional matrix, not two-dimensional, sorry, a two-column matrix with just the X and Y. This projection matrix just eliminates the Z. And actually, this will get us pretty far. In fact, this exact matrix is what's known as, is what's used for like orthographic projection. There's all different stereographic and all different kinds of projection matrices. This one is going to work just fine for us. So let's put this in our code. All right, actually, before I do that, let me just go back, and I'm just going to, by the way, ordinarily, right, if I were using P3D, let me just go back and put P3D back in there. If I say print, all the while, processing is keeping track of a matrix behind the scenes to do all this for you. That's what P3D is doing for you. So if I had print matrix right here, whoa, look what we got. Oh, whoa. Wait, why do I have this crazy? Oh, it has more stuff in it because it's doing other fancy things. Oh, maybe I went off on a little tangent here. Oh, Simon is giving me a good way to create a class called polyhedron. Yeah, that's going to be useful for me. Thank you. Wait a second. I guess I don't want to reveal this. Yeah, because someone remind me why it's 4 dimensions because of the 4x4. And does this translate? Do I have a rotate in here? Is that why I had some weird numbers there in the back? Yeah. No, what are these? This is like the Z clipping plane or something? The fourth element is the transparency. Really? No, but that's in the color. All right, I'm not going to worry about this. I'm not going to go off on that. I thought that would be interesting to show the connection, but I'm going to leave that out. Okay. Homogeneous coordinates. Okay, Sushnata points out that's totally right. So I'm not going to use homogeneous coordinates because that's they allow common vector operations as translation, rotation, scaling, perspective to be represented as a matrix. So I'm doing them separately. I'm using separate matrices, and this uses homogeneous coordinates. So I wonder. I think I won't open that up right now. It's an interesting aside, but I'm going to leave it out. All right. Let me just cycle the camera. Okay. Okay, so the first thing that I need to do is I need to create that projection matrix. And this is actually an easy thing. Now, of course, if I were doing this in a more sort of robust way, I'd probably have like a matrix math library. I just have a few matrix math functions that are in this tab that I wrote in a previous video. So I'm going to make a projection matrix, and I'm going to just make it as a two-dimensional array. So 1, 0, 0, comma, 0, 1, 0. So this is my representation of a 2-row by 3-column matrix. 2-row by 3-column matrix that is this right here, represented as a two-dimensional array. Now, what I'm going to do here is I am going to say for every point, for every 3D point here, let me move this over a little bit, I am going to, oh, whoops, I was futzing and I put P3D back in there. Take that out, no P3D. I am going to say okay, I'm going to say I want to get, so I'm thinking about this. All right. Timeout. I'm going to add another helper function. Matrix to vec, right? Because really, if I'm going to change this, right? Like this is the helper function I want because I want to receive the matrix and the vector, convert the vector to a matrix, multiply it, and then convert it back to a vector. Yeah. Okay. So what I want to do, so what I want to do here for every single 3D point, right, is, and this was sort of pointless that I did before. What I want to do is I want to create a p vector. I'm going to call it the projected 2D vector. And what I'm going to do is I'm going to say matrix multiply the projection times v. So this is what I want to do. To project a 3D point into 2D, I need a projection matrix, which I just made, and then I need to matrix multiply the projection matrix and the vector. Now, how the math for that works involves this times this plus this times this plus this times this goes here, and this times this plus this times this plus this. I'll refer you to matrixmultiplication.xyz. That website has a nice visualization, and I've made other videos about how matrix multiplication works, which I'll also link to. But I'm just going to assume that matrix multiplication works. And you can see how this makes sense. This one leaves us only with the x. This one leaves us only with the y. So now I'm going to then say point projected 2D x, projected 2D y. I probably could come up with a better name than that. And now if I run this, same exact thing, right? Because in this case, it's as if the point light and the place that I'm projecting onto and the thing, they're all like kind of in exactly the same spot. So there's no skewing. There's no skewing of the sort of perspective. So if I were to move that light around and change the projection matrix, different things can happen. But I'm not going to worry about that right now. What I want to do now is see if I can apply some rotation. Okay. So how do I apply rotation? Well, I know that I could just say like rotate by angle, right? If I say rotate by angle, processing is going to do that transformation for me. But what if I want to rotate x, rotate around the x-axis? I can't do that. I'm getting some sort of error somewhere or nothing. It should say not available with this renderer. Oh yeah, rotate x can only be used with a renderer that supports P3D. I need to write my own rotate x function. And guess what I need for that? Rotation matrix. I think the ding is better after. Guess what I need for that? Rotation matrix. Oh yeah, that was great. That was exactly what I meant to do. Okay, so now I am going to create a rotation matrix. Now, how does that work? Luckily for me, I already have this Wikipedia page opened up. Look at this. A rotation matrix is a matrix that is used to perform a rotation in Euclidean space. And this kind of makes sense, right? Look at this rotation matrix. Have you ever done one of those things where you do polar to Cartesian coordinate transformation and you take the angle and you keep increasing the angle and then you convert that to x and y points and you have this like spiraling thing? I've made videos where I do that. Basically, to rotate in 2 dimensions, this is all I need. So just for fun, let's first just do this. I'm going to say float. I'm going to make another. I'm going to call this rotation, and I'm going to make another matrix. And I'm going to do exactly this. It's going to be 2 by 2, and it's going to be cosine theta and negative sine theta. And I'm calling it angle. Cosine angle, negative sine angle. And then it's going to be, what was it? Sine angle, sine angle, cosine angle. Is that right? So this is, I didn't get this right. There's this needs a bracket. I don't know what I'm doing here. And this needs a bracket, right? It's a 2-dimensional matrix. There we go. Nope, semicolon. There we go. So this is my rotation matrix. This is my rotation matrix. So what now? What if I were to say, okay, now I'm going to take out this rotate x. I'm not using the native rotate function. And I'm going to say p vector rotated equals mat mul rotation times projected 2D. And now I'm going to draw the point at rotated. So I am projecting, V is a 3D vector. I'm projecting it into 2D, and then I'm rotating it, just a 2D rotation. And if we run this, okay, what's wrong? Columns of A must match rows of B. Oh boy, I made a problem. Indeed, we have a problem. Oh, this little clever demonstration. Okay. So I'm trying to be very clever, but it's not going to work because the truth of the matter is P vectors always have the Z, and I'm not accounting for that. So even though I just want to do a 2D rotation, where is that? Oh, I'm in the matrix, sorry. Okay, something horrible happens. I got columns of A must match rows of B. I made a mistake in my matrix multiplication thing. Here's the thing, I'm trying to be all clever to show you it in 2D first. The truth of the matter is P vectors, they're 3D. Even if I'm drawing just the X and Y, there's always that Z component. So I actually need to include this extra column with zeros in it to do this demonstration. So now you can see that's me doing 2D rotation. And actually, I'm actually doing 3D rotation, right? Because really, what this should be is this. This is what I would call XY rotation. I am rotating around the Z axis by, using the X and Y axes, right? Look at this. Now I'm going to say, so this is what, and if I kept scrolling down this Wikipedia page, we would see this. We would find this right here. This is the one that I'm doing. Rotation Z, right? Oh, I need a 1 there, of course. Not a 0 there. Very important. I don't want to lose the Z point. I want to rotate the X and Y axes around the Z axis, but I don't want to lose the Z point, so I need a 1 there. In the 2D case, okay, so I need this here. So this I'm going to call rotation Z. And now I'm going to make some other ones. Let's call them rotation X. And the rotation X is Y and Z. So I need to have my rotation values in the Y and Z spots. So hard to do this. I should just copy it from somewhere, but this will work. And I think this is right. So this should be, right? You can see this is, my spacing is off, help me. This was rotation Z, this is rotation X. And let's do one more. Let's do rotation Y. So I need to have 0, 1, 0 in the middle. The last one will be sine of angle, 0 cosine of angle, and the first one will be cosine of angle, negative sine of angle with a 0 in the middle. Okay, so this should all line up nicely. This is rotation Y. Do I have any syntax errors? Rotation Z, rotation X, rotation Y. Okay, now. So here's the thing. I'm going to do something terrible. What if I just put, like, if I put rotation z here. Oh, I have an error. Oh, I'm missing a comma here. Thank you. So I think I got it everywhere else. Right? That's rotation z. What if I try instead rotation x? Oh, weird that that's working. I guess it's oh, you know why it's working? It's working by accident, really, because my z points. So, but I've done something incorrect. But you can see this looks as if those 2 points, and I want my angle to move up a little bit faster. You could imagine this as a plane almost spinning around the x-axis. But here's the thing. I should be doing, the projection should happen at the last moment, right? I should really be rotating first. And then I should project the rotated vector. And so here, projection and so really, for it to be correct, it's got to be in this order, because what I need to do is first rotate and then work by accident because my z values are 0. But now, let's do something. Let's make 8 points. Again, I'm doing this in a highly manual way. Let's now have all these be at -50. I wonder if I want to put them, I think this will be fine, -50. And then now these all at 50, right? I basically, right, if you think about it, a point has 0 dimensions. A line has 2 dimensions with 2 points as the bounding box. A plane, a square, has 2 dimensions with 4 lines bounding it. And then a cube is in 3 dimensions with 6 planes. But really I can kind of make the cube just with 8 points, which are the edges, all those connections. So let me just run this for a second. Oh boy, this works too fast. I didn't want this to work so fast. So now we can see, let me just go back to rotate z. And look at this. That looks, now why do I not see 8 points? Because I'm using orthographic projection as if the light is right there. There's no kind of perspective. I'm not moving the light source away to create this kind of more 3D perspective look. I can't see when the points are right in front of each other, the shadow projects on exactly the same spot. But if I were to do rotate y, now you can see, you can kind of imagine that being a cube rotating. And here's now where I can get fancy. I can now say rotated equals mat mul rotation x times rotated. So I'm just going to do this a couple times. I'm going to just like keep rotating by all the different. So I'm going to do this as separate operations. Now there's a way I could probably combine all those, but I'm just going to do all of those matrix rotations. And here we go. Now we have my cube spinning along all axes. Now it doesn't look like a cube. Line 37. Time out. People are telling me to check line 37. 1 0 0 0 0 1. That's right. Wait. There's an extra 0? Where? Ah, here we go. It's line 43. Time out. In all of my futzing with this, I left an extra 0 here. This rotation x should be 1 0 0 0 cosine negative sine 0 sine cosine. All right. So hopefully that doesn't change much. It still looks right. So that probably was just being ignored. I was ignoring it, but I don't want that in my code. So now we can see we've got this rotation. The truth of the matter is I really want to draw this as a cube. Oh, I want to draw this as a cube. Let me think about this. There's got to be an easy. Obviously, I could manually connect all the points I want to connect. Also, this is not the same size as what I started with. So I'm going to just replace every 50 with 100. And every 50 with 100. That should work. Let's make that a bit bigger. There we go. So that's what I had originally. And I also was doing something with the angles. right? I was like doing like, I don't remember, but I had like angle times 2, angle times 2. So I could also vary the speed of the rotations. This is very silly what I'm doing right now and pointless. But I just wanted to match some more like what I started with. Okay, anyway, so you can kind of see that, and that's why it was moving. So then I had it as like 0.1. Okay, so this should now match exactly what I started with. All right. I'm thinking, I want to draw the edges here. I could have just replaced all the 50s with 100s. That's a very good point. Brain's melting. Is it 2 o'clock? No, I have 20 minutes. How do I want to draw these edges? I'm going to do it the lazy way, I think. You only need to add division to make a perspective. Yes, I know. I'm going to add division. But I need to add division. I need to remake the projection. This can't be global anymore. I need to add that in here. The code says how to draw the edges. What code? Oh, your code. Oh. Wait, I'm looking at Simon's code here. How do I make the edges? How do I make the edges? I know how to draw the edges by a line. But is there a nice algorithm if I have all the points of the cube written index 0 through 7 here? Like, I know which need to be connected to make all the planes. Do I have to how many edges are there total? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12, right? Draw 12 lines with your vertices as an index. Yeah. Right, I should definitely replace the 100. All right. Let me go back for a second. This is silly. Mathieu, let's not do that part where I change the angle and everything. Okay. All right. All right. Let me do something that's going to help us in the long run. What I actually want to do is, instead of using 50 all in here, I'm going to change every instance of 50 to just the number 1. So I'm going to kind of have normalize the cube. Actually, I kind of want to change it to 0.5. Instead of 1, I'm going to change it to, because I want the sides, the lines to be of length 1. So whoops, replace all. Ooh, I have 1s in other places. Bad idea. Hold on. I'm going to change all the instances of 50 to 0.5. Okay. So now if I were to run this, I don't see anything here. But very easily what I can do is at the last moment, I can scale things up. And again, I could do this with some kind of, I'm just going to do multiply each vector by 100, and then I have this. And if I multiply it by 200, then I have this, which more closely matches what I started with. The angle rotations are different, but that's no big deal. Okay, I wanted to do that because I also would like to show you perspective. And I think if all my coordinates are normalized, that's going to make it a little easier to do. But before I show you perspective, let me connect all the edges. So there's 12 edges. So in theory, I is less than 12, I plus plus. Right? What am I connecting? I'm connecting. Let me think about this. I'm connecting. If I say connect, what did I call the points? Let me just 0 and 0. Let me write a function. Let me write a function called connect, and it gets 2 p vectors, and it just draws a line. I'm going to say stroke weight 1, and it draws a line between one and the other. Stroke 255. So if I were to say connect, oh, and it doesn't get 2 p vectors, it gets 2 integers, and p vector A1 equals, I'm going to call this I and j. P vector A equals points I, and p vector B equals points j. This is like, so I should have a line between the first 2 points. How come I don't see that? Oh, wait. Yeah. Point O. Oh, I need to connect. I need to connect. Okay, so I'm going to make this p vector projected equals, I'm going to make an array that has 8 spots in it. And then, instead of drawing this here, I'm going to say projected. So now I really need to, this is fine. Int index equals 0. I could just use now a for loop, but index plus plus. Projected index equals projected 2D. So I'm going to put everything in an array, and then I'm going to say connect 0, 0 in projected. And then this will be an array of points. And so now this should, where's that line? Let me just make sure. Now if I say for p vector v in projected point, I really didn't want to draw the edges. This is why. I wanted to just leave it as that, leave it a viewer challenge to draw the edges. Projected 2D, projected index equals projected 2D, index plus plus, p vector v. Where's all that stroke weight stuff? This stuff should be here. Where am I drawing all the points? So, okay, there are the points again. Now, I want to connect 0 and 1. 0 and 1. There we go. It took me forever. So now I'm connecting 0 and 1. Then I want to connect 0 and 2. No. 0. Then I want to connect 1 and 0. That's the same thing. Connect 1 and 1. No. 1 and 2. This is good. Trial and error. This is fun. Then I'm going to connect 2 and 3. I just want to figure out if there's an algorithm for this. And right, because this is the plane. This is the first plane. 3 and 4. I see. So this makes sense. Whoops. No, 3 back to 0. That's the first plane. And then the next plane is the same thing, but at the end, which is like 4 to 5, 5 to 6. Oh, no, 3 to 4, 4 to, right? Because didn't I put the next plane would be 0, 1, 2, 3, 4. No. Yes. 4 to 5, 5 to 6, 6 to 7, and 7 back to 4. Okay, so that's that. Now all I need to do is connect. Oh, this is easy. So there's definitely an algorithm for this, because now I just want to connect 0 to 4, 1 to 5, right? 2 to 6. Hopefully the algorithm is revealing itself to you. And 7 to 8. No. 3 to 7. There we go. There's my cube. I have done it. Now, I should really refactor this, and I plan to do that, but right now I think I need a little bit of a break. All right, so, but this is really, actually, no, I don't. I got to do it right now. I'm sorry. This video is going to be really long. I don't care. I equals 0. I is less than 4. I plus plus. So what I'm going to do, right, there's 4 sides. I am going to connect I with I plus 1 modulus 4. Then I also want to connect projected. Then I also want to connect I plus 4 and I plus 1 modulus 4 plus 4. Let's do that. And then I just want to connect I with I plus 4. I think that's it. That's these 3 little blocks. Woohoo! Oh, I'm so glad that actually worked. Okay, so this is connecting the edges. This is going to really help when we have to do the, when we have to do the hypercube, connecting the edges. Okay, I should really go. I only have 10 more minutes in real lifetime while I'm recording this. But let's actually add perspective. Let's add perspective. How do you add perspective? Woo! So the way that you add perspective, perspective projection. Basically, we're going to add a variable. Whoops. We're going to add a variable which indicates the distance. Remember my ridiculous experiment earlier, like about 4.5 hours ago, if you are actually watching this video all the way to the end, where I had this light source and I was shining the light source and you were seeing the shadow here, that projection. I need a variable which is the distance away from the object, the surface, that light source is. That's how I get perspective projection, right? Somebody tell me that that's right. And then I should be all right. This is orthographic projection, which I have done already. Weak perspective projection, which is just plus a scaling. Perspective projection. Oh, wait a sec. I'm losing my mind here. This is what I want to do. Oh, blah, blah, blah. The way I did it was so easy. I don't want to do perspective projection. I was going to do it. I just want to do stereographic. Hold on. I might have to just not do this part right now. Because that's all I really need for, yeah, this is what I'm doing here. The value divided by 1 minus the distance. That's what I was doing. Can I just do that? Because one minus the z. Yeah. I dare you to do 4z, right? Yeah, 1 minus z distance. That's what I want. Like I just, right, hold on. Like basically, let me just do this for a second. Like basically what I want to do is take this here, and basically right before I do the projection, this should be 1 divided by 1 minus v dot z, right? And then z, right? Let me just, yeah, ooh. Right? And then this is like the distance, right? Because right? Isn't this what somebody confirm for me who actually knows this stuff? I have 5 more minutes. Because if I change this to 5, yeah, then the light's really far away. This is like the equivalent of the distance. Whoa, what horrible thing. But I guess it can't, right? Right? So this is like, yeah, I'm doing the tesseracts today. I'm coming back this afternoon. I'm going to do the tesseract. But this is like some build up to the tesseract. Right? So somebody confirm for me that correctly. I see very little activity in my reliable Slack channel. Alka's watching this. Alka must know the answer to this. So this would be basically, this is as if the light source, is the light source getting closer? Like this, is this called stereographic projection? Like, I just want to see this formula somewhere. It doesn't look right to me. Thanks, Alka. That's why I don't want to do it. I don't want to get into all of the simple. It's really like orthographic, but just moving the light source away. Blah. Weak projection. Weak perspective. I can do weak, which is just a weak perspective projection uses the principles of orthography but requires the scaling factor to be specified, thus ensuring that closer objects appear bigger in the projection and vice versa. You can see it's a hybrid between orthographic and perspective. And so the weak perspective model thus approximates perspective while using a simpler model similar to the pure unscaled or unscaled. So with these conditions, all points of the theory are at the same distance z from the camera without significant errors in the projection. So basically, what this is saying is just weak projection would be just scaling everything by z. So actually, like leave this. Oh, like this, basically. No? Z, average constant depth. Oh, it has to be rotated. Oh, whoops. No wonder. Ah. Yeah. Hold on. It has to be, the whole point of me putting this down here. Ah. The whole point of me putting this here was to do this. There we go. Oh, whoops. No, that's still orthographic. I'm like, why don't I see anything? There we go. That's stereographic projection. Now, if I want to move further away, yeah. Yes, this is what I meant to show. Aha, I got it. Okay. This is why you should look at the YouTube chat more often. Yeah, no kidding. All right. Now I forgot where I was in this discussion, but hold on. Okay. I'm going to come back to the code. So I just did my little demonstration over here. Okay, so So to create this idea of perspective, right, I want to move the light source or move the camera further away. There's a lot of different ways to do this in highly sophisticated methods, but basically I need to scale the x, y positions by the depth, right? Objects in this mirror appear closer than they really are. Like things that are further away appear closer in. Things that are closer further out. Appear further out. So to do that, this projection matrix can't just always be constants of 1 and 1 in the x and y positions. So I'm going to move this, and I'm going to, before I project, right? Before I project the final rotated matrix, I need to dynamically calculate this projection matrix according to the z value itself. So one thing that I could do is I could just say float z equals rotated dot z, and I could just try dividing by it. I'm sort of scaling it according to that z. Let's see what that does. Something, maybe it looks all weird and crazy. That's not right. Well, a nice formula for doing this is actually saying 1 divided by, this is now the distance, basically, the camera distance, the light source distance, minus rotated dot z. So if I put that in here now, and I were to say float distance equals 2, for example, now you can see this looks much more like perspective projection. So this is no longer orthographic, it's more like perspective, exactly sort of, again, I'm not saying that I've comprehensively solved every possible projection 3D way with focal length and all sorts of field of view stuff. I'm just doing something kind of basic. This is probably similar to weak projection maybe, I think. But you can see here if I change this distance to 1, now this object appears much closer, it's more distorted. If I were to change this to 10, wow, it's so far away, but you can see there it is. Those points are a little bit too big. Now, one thing I'm not doing is changing the stroke weight to make it seem further or smaller, but you can see I'm just altering the perspective. Okay, we've done it. Where's my train whistle? I need a train whistle. No train whistle for me. Maybe I'm going to reward myself with a piece of space melon. I have made this coding challenge. So what can you do? First of all, if you want to challenge to yourself, just go make this in 4 dimensions now. But that's what I'm going to do next. Now that I have successfully drawn a 3D cube, and just to prove the point, I am in the P2D renderer. The P2D renderer, using my own matrix math and my own rotation matrices. You don't need to do this. I would probably just go back and always use P3D. But this should let me unlock the 4th, the 5th, the 6th, the 7th dimension. Try making different shapes other than cubes. Try, you can do weird stuff. I probably get something super weird if I just, let's make the distance 2 again. And let's, change this negative to positive just for rotation y. And look what I've got going now. I can really start to distort the world by just messing around with these numbers. What if I say 5 times cosine of angle down here in rotation y? Okay, that's probably a terrible idea. So what kind of crazy, weird, distorted rotation perspective things can you do? Can you actually do this with vertices so you can apply fill? Can you think about color? Make some sort of weird, pretend 3D world that doesn't follow our own sense of 3 dimensions by playing with this code, and share that with me in the comments or on Twitter, and also on thecodingtrain.com. There'll be a link to the webpage where you can submit user-made things. Okay, my phone is ringing. It says, maybe Brian. I wonder if that's Simone's tumor calling me. Okay, goodbye. Continue to enjoy the YouTube thing, or go outside and do something else. I'll see you in a future coding challenge. Okay, I know I have to go to my meeting. I'm just going to be a little bit late. Okay. Really? I think it went to voicemail. Okay. Boy. What's the chance? My meeting's downstairs. I'm only going to be 5 minutes late. I don't think it's a problem. What's the chance That can be edited into like a 30-minute coding challenge. Maybe. Okay. All right, I've got to go. So this is going to end. This is the end of this particular live stream. What I'm going to do really quickly is I'm going to go to YouTube Studio. I'm going to create an event. Let me just email that I'm running a few minutes late. Hello, Marshall. Thank you for your contributions on GitHub, Marshall. Oh, did I freeze? No, I'm still here. Oh my God. Oh, yeah. Oh, yes. See you in 5 to 10 minutes. Okay, so I mean, this is a thing that I've really wanted to learn for a long time. This 3D stuff always seemed like impossible. I am going to I'm going to go to live streaming. Dopperon, are you live streaming right now? Sure, everyone can go watch. I'm going to go to events, new live event. Oh, wait. Actually, something I can do is I can duplicate shoot. I can say, how do I do this? There's a way to like duplicate new event from this one's settings. Let's see. I can't do that while it's live. I'm just going to do new live event. The Tesseract. Today at, let's say, 4 p.m. I think realistically I can be back here at 4 p.m. 4 p.m. to 6 p.m. Tesseract. Coding challenge. Public. Advanced settings. Slow mode. Make archive unlisted. Blah, 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 blah. Create event. Okay. So in theory, I'm pasting now into the chat the next, I don't know where the chat went. Here it is. This is the next event. All right. Okay, so, all right, so I'm going to go. I'm going to be back later. I'm going to make this Tesseract thing. I mean, this is so not going to be true, but in a way, I almost feel like it's going to be easier having done this. First video. So we'll see. Oh, did it do 4 p.m.? Did I set it to 4 p.m. Pacific by accident? Let me see. No. 4 p.m. Eastern. All right. So, and in Slack channel, patron, sponsor, member, YouTube thing is called memberships now. I could also potentially, if there's any like filler stuff or intro or outro-y stuff that I need to do, I'm thinking actually maybe it sort of makes sense that there's 3 coding challenges. There's a coding challenge that's just matrix multiplication, and there's a coding challenge that's like 3D projection and 2D. What's a good like SEO term for what I just did? Normally I don't like to think that way, but I feel like people searching for a video about how to do the sort of basics of 3D rendering in a 2D canvas is kind of like a thing people often look for. And there's maybe a term for that. I don't want to mislead people that I'm like doing, ray tracing, for example. But so if anybody has suggestions for that, tweet that at me, or particularly if you're a member or patron, mention that in the Slack channel. And if Mathieu is around, we can message Mathieu. Often has good feedback of like, oh, record some extra intro, outro-y stuff. All right, so I'm going to hit the stop streaming button. And I will see you. I got to finish my melon. Oh no, maybe I can save it till this afternoon. Won't go bad, will it? and I will see you all in a little less than 2 hours. Apologies if I'm a little late to this afternoon one. Okay? I'm going to hit stop streaming and hit OK. Oh, actually.